In this video, we'll be talking about phase shift, and right now I'm just going to introduce what a phase shift is, but later on in the video there will be problems for you guys to do, which will probably be more helpful than me telling you what a phase shift is. But what is a phase shift? Well, the formula for position in oscillating motion is your amplitude times the cosine of angular frequency plus theta. Now you might sometimes see this component of your formula being phi. Another way to write phi is like so, right? But basically, all in all, theta, phi, same thing. They're just your phase shift, the phase shift component of your formula. And in all your formulas in oscillating motion, including velocity and acceleration, all of them have a phase shift. And you need to include the velocity and the position to make sure that your phase shift or phase angle that you got was right. And I'll show you the reason why for that later on in your problems. But basically, the overall gist of it is that your position function, let's say x of t is written down here, is a cosine wave. So this cosine wave has some amplitude and some shift, right? And right now the shift is 0 since the cosine wave starts at 1 at the x equals 0 point. Actually, t equals 0 point in this case. So right now your phase shift is nothing. But what do you do when there is a phase shift? Well, if there is a phase shift, it either moves this entire wave to the left. So if this wave was moved to the left, let's say it looks something like this, right? Okay, that's wrong. It would look something like this. All right. So basically all I did here was move this entire wave to the left. So I move all this in red to the left, and then what you get is the green. But if you subtract some phase, so let's say you subtract a phase, well, this thing moves to the right. So let's erase the green so it's less confusing. This sine wave moves to the right, so that means now the top can start at maybe here. You can draw your wave like this. So basically, all a phase shift does is move your cosine wave or sine wave to the left or to the right. But it's important to note that when you're solving for the phase shift of just your x or your position function, you need to take in consideration the phase shift in your velocity function, because when you are solving for it, you're going to use inverse cosine or inverse sine. And now here's the thing about inverse cosine and inverse sine. They have limited values that they can output. So I'm going to cover those bases in the problems that we're going to do right now. So right now I'm updating Rainbow Six Siege. Right now it's the Siege X update. It's the largest update of like literally all of Siege time. And like sometimes I mention the game like when I'm playing, when I'm recording these YouTube videos. So maybe some of you know that I play the game pretty consistently. Biggest update. Can't wait to play it after I finish this video. But let's go ahead and do this problem. So we've something in simple harmonic motion. Doesn't matter what that thing is. And we have an angular frequency of 2 radians per second. At time equals 0, the position of the object is at 10 meters, and the velocity is going at 13.27 meters per second. The amplitude is 12 meters. So find the phase shift. How do you find the phase shift given this information? Well, the phase shift inside of the position formula is marked by the theta value. So we actually have enough information to complete this equation, except for theta. So what is x of t? Well, x of t at t equals 0 is at 10 meters. So we can plug in 10 here. So the position is at 10 meters when time is equal to 0. The amplitude is 12, and the cosine is angular frequency times time. But since time is 0, it cancels out the angular frequency. Therefore, the only term inside of this cosine value is your theta value. And then we can actually solve for theta by just isolating theta using inverse cosine. So if you inverse cosine both the sides of the equation here, you should get, so arc cosine of 10 to the power of 12. You should get 0.586 radians. And we're using radians, not degrees, because the units that we're using is radians per second, right? For your angular frequency and all the other things, radians. So we're going to use radians in this problem rather than degrees. But if you want to turn this to degrees for easier understanding, it's 33.556 degrees. So here's the thing about arc cosine. Arc cosine has a limited range of 0 to, so the output is limited from 0 to pi. That's the output for arc cosine. So if you have a unit circle, arc cosine can only output the degrees on this side, the top half of your unit circle. And let's say this is the y-axis and this is the x-axis. Or if you want this in degrees, it's also limited from 0 to 180 degrees. So right now we have 33.56 degrees. Looks maybe something approximately like this. And we'll represent it by theta. Well, if you were to flip this value over the x-axis, so you flip 33.56 degrees over the x-axis, you would get 360 minus 33.56 degrees, which is equal to 326.44 degrees. Now, why do we have to take this into account? Well, we have to take this angle, theta, or green, the green one, into account because the range of arc cosine is limited from 0 to 180 degrees. So it can only measure the cosine values or the theta values on the top half of your circle. So it doesn't take into account the bottom half. Even though the answer for both of these, so the cosine of 33.56 is equal to the cosine of 326.44. And the reason why these are equal is because cosine is equal to the adjacent over the hypotenuse. And on this side of your cosine unit circle, the x value is positive, or the adjacent value is positive. So if the adjacent is positive and the hypotenuse is always positive, then on both of these triangles, or on both of these unit circle representations of your angle, it will be equal to the same answer since both of these adjacents are the same and the hypotenuse is always 1 in a unit circle. So we need to take into account the other side, the flipped x-axis. And how do you do that? Well, we can write it down in velocity. So let's write down the velocity formula. Let's solve for the phase shift with the velocity formula. So the velocity formula is negative amplitude times your angular frequency times the sine of your angular frequency times time plus theta. So if we just plug everything in, well, at time equals 0, your velocity is 13.27 meters per second. Your amplitude is always at 12. Your angular frequency is given by 2 radians per second, and the sine value is given by just theta because time is equal to 0, so the angular frequency inside the sine function cancels out into 0. So both of these turn to 0, and we get left off with 13.27 is equal to negative 24 sine of theta. Now we solve for the theta value here, right? The theta value in our position function is 33.56 degrees or 0.586 radians. So let's plug 0.568 radians into a calculator. So let's put negative 24 sine of 0.586 radians. And what you get actually isn't the right answer. So the right answer is 13.27, but you got negative 13.27. So currently, and the negative matters here, currently your phase shift is wrong. But what about for the sine value? Let's try to isolate. Let's try to isolate your sine function. So let's try to isolate the theta value in your sine function. So 13.27 divided by negative 24 is equal to sine of theta. So if we arc sine both sides, so arc sine of 13.27 divided by negative 24, you get a radians value of negative 586. So what did I say about your unit circle? Well, your unit circle reflected across the x-axis for the cosine value will both have the same cosine value using your arc sine. using arcsine. Using arcsine only limits your range from 0 to 180. But the answer, when you reflect your theta value over the x-axis, is still the same as your previous non-reflected angle. So we have negative 0.586 radians, which is the negative of 0.586. So the answer of negative 0.586 when you plug into a cosine value is still the same as just putting the positive version of this. Which one is the true right answer for the phase shift? Well, it's negative, because if you plug in, so let's say 10 over 12 is equal to the cosine of negative 0.586. Well, if you plug in cosine of negative 0.586 into your calculator in radians, of course, you will get 10 over 12. And if you plug in negative 0.586 into your sine value, you will get 13.27 divided by negative 24. You will get negative 0.553. So the true right answer, the true theta value, or the phase shift, that works for both your position function and your velocity function is negative 0.586. So for this problem, I didn't give you any word problem or nothing like that. I'm just going to give you the necessary information. So let's set up the equation again. So x of t is equal to your amplitude times the cosine of your angular frequency times time plus theta. Well, in this moment, your time is equal to 0, so we can cancel out your angular frequency part of your position function. Your amplitude is equal to 5, so we write down the cosine of theta is equal to, well, at t equals 0, your position is equal to 4, so 4 over 5 is equal to cosine of theta. All right, let's plug in arc cosine into 4 over 5. If you arc cosine 4 over 5, you should get 0.643 radians, 644 radians as your radians answer for now, but we need to test out the velocity function as well. So the velocity function is negative amplitude times angular frequency times the sine of angular frequency, not times, the sine of angular frequency times time plus theta. So let's set up this equation. Negative 9 meters per second with an amplitude of 5 with an angular frequency of 3. Sine of, well, again, t is equal to 0, so angular frequency cancels out inside of the sine function, and you get left off with theta. So what you have right here is 9 over 15 is equal to sine of theta. So let's test out inverse sine of 9 over 15. Well, inverse sine, or arc sine of 9 over 15 is equal to 0.644 radians as well. So since these two match up, we don't have to flip the cosine value over anything. So basically, you just need to do some algebra and some trig with both the position and velocity formulas. Just make sure that at the end, when you plug in t of 0 and their corresponding values of position and velocity, you get the same theta value. And if you don't get the same answer, just test your sine answer into both the theta values of your cosine and sine functions. Or test out your arc cosine value into both of the sine and cosine functions that you get. Just substitute things until you find one that works. But as always, I need to mention OpenStax. I get my problems from there. Online textbook. It's great. Link will be down in the description. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.